Hi, so welcome back to our channel, and today we want to look at the goodness of fit test. So what is the goodness of fit test? It's just basically a test that we use to see if the data we have, if it matches some kind of pattern that was previously assumed or some pattern in theory. So to help you with this example, we're going to use is of products that were damaged or products that have defects during the manufacturing process. So here in our data set we have two variables. So we have the shift and we have defect. So the first variable is the shift on which the defect was found, and also here the variable here defect is a type of defect. So let's say this data set, which has a pretty good size, and I want you to know that this data set, okay, so it has 365 entries. I want you to know that this data set is a fictitious data set, right? So we want to look at it and we want to find out. So say for example it was expected that the frequency of defects for each shift was expected to be the same. It didn't expect the morning, evening, or the night shift to have any large differences in frequency. And there's a way you could use PSPP to test this. But before we do the goodness of fit test, let's look at some of the requirements for this test. Alright, so as stated before, right, the null hypothesis in this situation when we're doing a goodness of fit test, which as you can see is a chi-square test and it's a non-parametric test, the null hypothesis is that the frequency of counts agrees with a claim distribution, as I had explained before, and the alternate hypothesis would be that the frequency of counts do not agree with that claim distribution. So what are some of the requirements? So if you're using sample data to make inference about a population, ensure that the data was randomly selected, and the sample data should consist of frequency counts for each category, and for each category the expected frequency is expected to be at least 5 to ensure that, you know, the test was stable and that the results are trustworthy. So what we mean by this, so for example in our data set, so for example again in our data set you would see that we have 3 shifts. So it's expected that you have counts for each shift. So it would make sense we're looking at morning, evening, and night, and then there was no counts for night shift. And you have to ensure that each shift has at least 5 counts or 5 defects were found during each shift. So how do we perform this test now? So what we do, we go to Analyze, go to Non-Parametric, and we'll go to chi-square. So here we see the interface here. What we're doing in this interface. So we're looking for production shift. I will send it across the test variables. So here we say expected range, and it's a get from the data, so you leave that as is. And remember, we're assuming that all categories are equal or equally likely, because there are 2 different ways to look at goodness of fit, and today we're looking at if all categories are equally likely. And after that, next thing we'll do is press OK. So here we have our output in Output Viewer. So it shows us the observed frequency. So 91 defects were on the morning shift, 110 were on the evening, and 164 on the night. And here we have the expected distribution if the null hypothesis was indeed true. And then when you look here at the residual, you could see the differences between what's observed and what's expected. So we could actually see that some differences here are large. So if you look at the p-value right here, you get a p-value that's less than or alpha of 0.05. So with that, we would reject the null hypothesis that states that the frequency of the counts of defects for each shift are equally likely. And the results, as I say, if you look at the results here, the results will show that they are not equally likely. There's huge differences between what's observed and what was expected. And that is how you perform the goodness of fit tests when you assume that the frequencies of the different categories are equally likely.